Hello and welcome. This is going to be our lecture video for February 10th through 11th. Let's go ahead and get started. Copy this down into our notes and attempt to solve it on your own. You consider pausing the video here and seeing if you can solve it. All right, so if we have exponents on both sides that have a variable in them, pretty much our only hope is to get the bases to match so that we can get rid of the base on both sides. So I got to think, can I rewrite 1/9 and 27 with the same base? And I can. I can rewrite the 1/9 as 3 to the negative 2, because 3 to the negative 2 would be the same as 1 over 3 squared, and 3 squared is 9. So 3 to the negative 2 is equal to 1/9. Let's keep the rest of that exponent. And then 27, that is 3 cubed to the negative 5x. So rewrite with same base. All right, and then we're going to use our properties of exponents to multiply these exponents. Power to a power, you multiply the exponents. And we get 3 to the negative 6x minus 4 equals 3 to the negative 15x. Now, at this point, I would normally say just drop the base, but what we can do is we can show a mathematical step here where we take log base 3 of both sides. So we are allowed to take the logarithm of the same base of both sides, and that's the mathematical way of showing how we're able to drop those bases. So take log base 3 of both sides, log base 3 of 3 to the negative 6x minus 4, that exponent could jump out in front, and log base 3 of 3 is a 1. So essentially, it just cancels that out. Negative 6x minus 4 equals negative 15x. And solve for x. Let's add 6x to both sides. We get negative 4 equals negative 9x. Divide both sides by negative 9. And we get x equals 4 over 9. The negatives cancel out. All right. Plug it back in, make sure it balances. Here we go. Goal for today is to find the inverse of exponential functions and use that information to graph logarithms. Why are we doing this? This will help us understand where the vertical asymptote comes from on a logarithmic graph. So, graph the inverse. Well, let's graph the original function and the inverse. So to graph f of x equals 4 times 2 to the x plus 1, I look at the end first. That plus 1 tells me where my horizontal asymptote is going to be. It's going to be at the line y equals 1. Then the 4 is my starting value. We say that's Alice's height, but she's standing on a 1-foot table, so her head is up here at 5. And then as I move to the right, I'm going to double each time. So next she will be up at 9, and I'm going to try to plot about where that would be. That would be 1, 9. So she's 8 feet tall, standing on a 1-foot table. And then going backwards, if it's doubling as we move forward, it's going to be cut in half as we move backwards. So 4 goes to 2, goes to 1, goes to a half, a fourth, an eighth, a 16th, a 32nd, as we move to the left. So there we have our graph of y equals 4 times 2 to the x plus 1. All right, now to find the inverse of this function, we're going to rewrite it with a y equals first. Then we're going to swap x and y. And we get x equals 4 times 2 to the y plus 1. We will then subtract 1 from both sides. X minus 1 equals 4 times 2 to the y. Divide both sides by 4. get x minus 1 all over 4 equals 2 to the y. And isolate the y. Y is in the exponents, so we know we're going to have to use a logarithm here. Log base 2, base of the exponent becomes the base of the log, of x minus 1 all over 4 equals y. And there's a way to simplify this. Whenever I see division or multiplication within the argument, I can split that up using the properties of logarithms. So this could be log base 2 of x minus 1 minus log base 2 of 4. And log base 2 of 4, that has a value. 2 to what power equals 4? 2 to the second power equals 4. So we could, as a final step, turn that log base 2 of 4 into just a 2. So log base 2 of x minus 1 minus 2. And now let's write it with function notation. So f to the negative 1 of x equals log base 2 of x minus 1 minus 2. Now to graph the inverse, we can just invert every single point here. Every x comma y becomes a y comma x. So 0 comma 5 becomes 5 comma 0. 1 comma 9 becomes 9 comma 1. We'll say it's kind of down over here. 9 comma 1. Negative 1 comma 3 becomes 3 comma negative 1. Negative 2 comma 2 becomes 2 comma negative 2. Negative 3 comma 1.5 becomes 1.5 comma negative 3. And you'll see if we just keep inverting these, we eventually start approaching a vertical line. The asymptote itself can be inverted. Instead of being the line y equals 1, it can become the line x equals 1, which is this vertical line here. And now this graph looks like this. It's a vertical line. It does extend down to negative infinity. Stays very close to that line until it comes over here. Then it starts going up. It never flattens out though. It just it decreases in slope forever, but it never flattens out. Okay. One way we talked about graphing these was in terms of transformations. Let's see, do we see that this graph has been shifted 1 to the right and 2 down? Well, the vertical asymptote of a logarithmic graph is normally along the y-axis, so it does look like that's been moved 1 to the right. And we said that every unshifted graph of any base of a logarithm has a point at 1 comma 0. Is there a point that has been moved right 1, down 2? And yes, that's this point right here. Ended up right there. All right, but by doing it this way, we were able to get many more points on this graph. And do notice that this is symmetrical over the line y equals x. There's your axis of symmetry. AOS, axis of symmetry. All right, find the inverse in the domain and range of the inverse. So in order to find the inverse, if it's given as a y equals, we can just immediately swap the x and the y. All right, now we're going to isolate the y, so I'll start by subtracting 9 from both sides. I get x minus 9 equals 10 to the y. Now rearrange this into a logarithm, so log base 10 of x minus 9 equals y, which I'm going to rewrite in a couple of ways. I'm going to bring the y to the left-hand side. I'm say y equals log of x minus 9. Notice I didn't write the base 10. The base 10 is assumed. If we ever don't write a base, it's assumed to be a 10. All right, the range of this, the range of all logarithmic functions is going to be y equals all real numbers. This does extend all the way up to positive infinity, all the way down to negative infinity, hitting every number in between. But the domain is limited. We cannot plug in 0 or a negative. So this value here, x minus 9, must remain greater than 0. If I add 9 to both sides, I get that x must be greater than 9, and that is my domain. Domain, range, there's the inverse. All right, the range of the original function would be that y is greater than 9, and the domain of the original function would be that x equals all real numbers. Domain and range switch whenever you find the inverse. All right, I'll embed a few more for you to try here. That's that for this lecture video. Have a great rest of your day.